So the problem that we're working on involves building a rectangle that's subdivided into 4 equal rectangles or partitions. And we want to maximize the area of this entire pen. So we know that altogether the farmer has 750 yards of fencing. So if I want to call each of these X, you can see that I need 5 sets of fencing in that direction, and then I can call this Y for right now. I need 2 Ys. So altogether, I know that I have 5 X's plus 2 Ys, and that's going to be equal to the entire 750 yards. So it's two of these plus 5 of those makes the entire 750 yards. Now, the important thing that I want to make known and understood with the dynamic aspect of the applet is that X and Y are not independent. In fact, Y is completely dependent on X. So if, for example, we made it only this high, then in order to use that entire 750, it might look more like that. I obviously don't know because I can't draw it like the computer can. So our goal is to get a visualization on the computer that's more accurate. So we have this right here so far. So the idea here is now I still have 5 X's and 2 Y's, but they're different values for the X and the Y. Again, what we want to do is emphasize that the Y is not independent. In fact, if we solve for Y, we get this, 750 minus 5X, and then we'll divide both sides by 2, and this becomes an expression. So instead of calling it Y, I'm actually going to call it G of X, and I'm going to say that G of X is a function of X. So I'm calling this, instead of calling it Y, that should be Y. This should have been Y, and I'm letting that be equal to G of X. Another thing to notice is that we want to maximize the area of this whole thing. And maximizing the area of the whole thing also maximizes the area of the individual squares, or rectangles anyway. So the area for the whole is G of X, the length times the width. So it's G of X times X. So I could even make this be a different function. I could say area of X is equal to G of X times F of X, where F of X is just equal to X. So now the next thing we want to do, algebraically speaking, is to transfer this area formula into just X. So we have the area of X is equal to G of X, which is this, 750 minus 5X over 2 times F of X, which is just X. So this is basically our parabola. And we know we can multiply it out. You're going to get what's half of 750? That'd be 375. So 375 minus 375x minus 5 halves x squared. Notice if it's a negative x squared term, it's an upside down parabola. And these are the 2 factors. So one factor is x, so we can imagine one factor is x, so then one root is 0, and this is the other factor. So if I set this equal to 0, that's when 750 minus 5x is equal to 0. So 750 minus 5x is equal to 0, so 750 is equal to 5x, so x is equal to, this goes into 7 once, goes into 25 5 times, so x is 150. Divided by 2. So we get 75. Okay, so no, I'm sorry, the root is going to be at 150. So the root is there's root at 150 and there's a root here. And it's going to look something like that. And we know that the equation for the vertex is negative b over 2a for the x coordinate, which is also halfway between 0 and 150. So we know that at 75 feet, this function is going to have a maximum. But we want to be able to build an applet that will show us exactly what we're talking about here. Let me go back to this, I apologize. What I was trying to get to is that in order for this root to be 0, the numerator has to be 0. That's why I said just that part equal to 0. It doesn't matter about the 2 because you really just want the numerator to be 0. So if we take this equation, now it starts getting messy. But this is the basic idea. So what I'm thinking about in my applet is that I want to have a graph and I want to have a dynamic figure. So maybe I'll have the graph sort of on the left-hand side of the screen, and I'll build my dynamic figure on the right-hand side of the screen. In the next video, I'll talk about how I plan to make the applet.